We're going to take a look at problem 14 from Projectiles Launched at Angles. A ball is thrown from a building that is 60 meters high. So the building here is 60 meters. You can see that's in our negative 60 for our y direction. It's thrown with a velocity of 28 meters per second. That's our hypotenuse at an angle of 25 degrees above the horizontal. We're going to find when the ball hits the ground. So that's going to be the time it takes to reach the ground sometime later. How far from the base of the building the ball hits the ground. So that's displacement in the x direction. How far above the ground the ball goes. So that's going to be maximum height. And the velocity of the ball as it hits the ground. We're going to have to do a couple of these separately, but what we can do in one go is how long it takes the ball to hit the ground and then how far it goes in the x direction, because that's one trip. The total time it takes to go up and come back down and hit the ground would be total time, and that would also give me this, and that trip is its maximum x distance, so we can look for that as well. First thing that we should do, though, is solve for the velocity in the x and the velocity in the y at the beginning of the problem. Velocity in the x is the adjacent side, so I'm going to use cosine of 25 degrees times the hypotenuse 28 to get a velocity of 25.4, and you can see I wrote that here in the x column. In the y column, the y velocity is the opposite side, so I'm going to use sine of 25 times the hypotenuse 28 to get an initial velocity in the y direction of 11.8, and you can see that here in my y column. First thing we're going to solve for is when this thing is going to hit the ground. I know displacement in the y is negative 60. Initial velocity is 11.8 and acceleration negative 9.8. So I can use this third equation, d equals v naught t plus 1 half at squared, and solve for time. Because time's in two different spots and one of them squared, I am going to use the quadratic formula on this equation, which we talked about before. The quadratic formula solving for t is t equals negative v naught plus or minus the square root of v naught squared plus 2ad divided by a. We can plug in the numbers that we have up here in our column, plug this into our calculator, and we get two options. Either the time is negative 2.5 seconds or it's 4.9 seconds. Obviously, negative time doesn't make any sense, so the correct answer is 4.9 seconds. Using that time, we can find the displacement in the x after this ball has traveled that entire time when it would get down to the ground 60 meters below the building, just by going displacement equals velocity multiplied by time. We solve for the velocity of the x in the beginning, 25.4 meters per second, multiplied by the time we just found, 4.9 seconds, tells me the distance that this is going to travel in the x direction is 124.5 meters. Since we are looking for the velocity when this thing is going to hit the ground, I want the final velocity in the y direction, so I solve for that here in this column as well. The final velocity of the ball in the y direction when it gets to the ground is going to equal the initial velocity plus the acceleration multiplied by the time. We know the acceleration is 11.8 meters per second. We solved that right here in the beginning, and we wrote that in our initial velocity. So 11.8 meters per second for initial velocity, acceleration negative 9.8, and the time is 4.9 seconds. That tells us that the ball is going to be moving downward 36.2 meters per second when it gets to the ground. Don't forget, it will have this horizontal velocity of 25.4 as well. Now for maximum height, we actually have to do a separate problem. The reason for that is, if we look up here, I have d equals negative 60. That's when it gets to the ground. I want to know when it's going to go up, up, up and reach its highest possible point. That's a different set of initial conditions. That's a different set of x and y. While the velocity in the x direction will be the same, the initial velocity in the y direction will be the same because here's where it started. But if up here is where it ends, then my final velocity in the y would be 0. My displacement in the y would certainly not be negative 60 because it's not down 60, it's some point higher. And while we solve for 124.5, that's how far from the building it lands on the ground. It's going to be something much less when it reaches its highest point. So we have to set up our x and y columns for the maximum height. Again, we know the initial velocities are the same. X is 25.4, y is 11.8. Now final velocity is 0 at the maximum height. Acceleration is always negative 9.8 meters per second squared. And we're trying to find how high this thing goes, so d in the y direction is our question mark. We don't know how long it takes to get to the maximum height, so we're going to use the equation without time, which is this fourth equation, vf squared equals v naught squared plus 2ad. A little bit of algebra. We're going to move the v naught squared over to the left side, giving us vf squared minus v naught squared, and then divide 2a away from the d, putting 2a in the denominator. That gets us the distance in the y direction equals 0 squared minus 11.8 squared divided by 2 times negative 9.8. Plug that into our calculator and we find out it's going to go 7.1 meters higher than when it was thrown. So if you wanted to add in 7.1 meters higher than the initial throw spot, that's fine. 7.1 meters higher than the building, that also works. Or if you're going to go from the ground, 67.1 meters above the ground.